Our lecture is going to be on gravitational waves and merging black holes. We're going to be talking about some of the most explosive events in the universe. And I'm not able to advance my slides.
Click on the screen. Anywhere.
Okay. Let's see if it doesn't work now. Yeah, okay. All right. So we're going to talk about merging black holes and the gravitational waves. So the lecture today, the first half is going to be about just waves in general. So we have a little bit of background to see how this all works. Then there is an amazing instrument called LIGO, which detects these merging black holes. And that was successful, and I'll discuss that. And after the break, we'll talk about black hole mergers in detail, talk about neutron stars, and finally, some future work. So we've talked several times now about this view of gravity being bending space. And I've shown this slide, which is kind of a way to view it in two dimensions several times. But now you can also imagine, though, that if we wiggled that out, if we wiggled the Earth a little bit, that then the space itself would also wiggle. And it wiggles in the same way that light, in somewhat, well, and actually quite similar to the way the light transmits through space. Namely, the wiggles move out like sort of water waves, and they carry energy with them. Okay, so they carry energy with them just the way light carries energy with it going through space. And these are gravitational waves. Now, this is okay. Let me see if I back up here. Okay, this is something you're quite familiar with, dropping a rock into a pond. And I want to illustrate these exotic waves, like light waves and gravitational waves, by something familiar, water waves. Because waves are waves, and in many ways, they act similarly. Now, there's a complication here. I want to show several videos that I got from YouTube, but YouTube has just changed the way it does things. It no longer lets, at least me, download things. And I have to go to the YouTube website and then show it on the YouTube website and then come back. And that involves several clicks, and I'll probably goof it up more than once. And it also shows the dumb ads and stuff that YouTube has. So just please be tolerant of this. This is going to happen. Okay. So now this is what you're familiar with. Waves coming out from central disturbance. This is what I don't like. Okay, I have to escape, I think. Yeah. No. Just oh, that'll probably goof. Oh, dear. The lower right has a little shrink it. Where? Lower right? Lower right. Just make it smaller and kill it. The two. Yeah, there you go. Yeah. Okay, let's kill it. Oh, yeah, all right. Okay, that's. And then share the slides again. There you go. Okay. Now, one of the things you notice, I don't want to show it again, but one of the things you might have noticed that the waves go out, and in water waves, you could see, in fact, you can see here, that the big waves go faster than the little waves, than the short wavelengths. That's actually, even though I like to use water to show it, water in some ways is more complicated than light waves through vacuum. And one of the reasons is this, what's called dispersion, namely waves of different speed travel at different rates in water. But in light and vacuum, all the wavelengths, all the colors travel at exactly the same speed. So that makes it actually easier. Same is true of gravity waves. So get to them. So the waves in space-time, will be something like this. We're going to have two objects that circle each other. And just as if we had two electrons, say, circling each other, they will cause waves. And they cause these waves in space-time. They bend space-time, space, just think of space, into these wave-like patterns. And that was a theoretical prediction by Albert Einstein in 1916. It's one of the early things that he derived from his new theory of general relativity, that there would be waves. But what he calculated, and calculated correctly, is that they are extremely weak. And I'll try to give some idea of that in a minute. But they are extremely weak, and so weak that Einstein said we'll never detect them. But it came sort of backward. People looked at the numbers, they were right, and they said we have no hope of detecting it. But starting in 1960 and 1970s, people started thinking about this. Maybe there's some way we could actually get at this. And
Roger, you might want to no, go ahead, play the video.
what's going on here? Why am I this worked at home? I'm having trouble with it here.
And go back.
Yeah. And if I push here, there,
Yeah,
just
so play, and then we'll do what we did before, which is kill the YouTube and then go back to the
Yeah.
video.
Okay, so here's an animation of that. I knew this would be a problem. But here's an animation of how that works. Two objects, and they're going to have to be big objects because these are very weak things, are going to combine and form a new object, a new black hole, as it will turn out. Oh, for crap. Okay. Now, I try to give you some idea of how weak these are, what the challenge is. That imagine a rod that's 2.5 miles long. Okay, there's a reason for that. And imagine a rod that's 2.5 miles long. And a gravitational wave can stretch that rod. That's what gravitational waves do. And we call that the strain, right? When you have a rubber band or a rod that you're used to, and you pull on it, that's the strain on it. And that's the fractional length that it changes. But the 2.5 mile long rod with a gravitational wave of the kind we can accept will only stretch by about a 10 trillionth of a centimeter. 1/10 trillionth of a centimeter. So this is extremely small. And this is why people thought this is hopeless, right? I mean, a 10 trillionth of a centimeter is smaller than a proton. It's the elementary particle of a proton. Smaller than a nucleus of an atom. It's smaller than one of the particles in the nucleus. Well, here's the device that is going to do that. It's called the Laser Interferometer Gravitational Wave Observatory, LIGO, and I'll keep saying LIGO from now on. And this is located in Louisiana. This was constructed starting in the 1990s, based on a lot of earlier research, and started working in about 2010. And these arms are 2.5 miles long. And that's the rod that I was talking about. And I'll tell you in a minute why they have these arms. So here we go again. Do this.
Is there a video link in there? There you go.
I don't know why it comes up sometimes, and sometimes it seems not to us.
Just don't annoy you, man.
Yeah. Oh, no, I don't have any sound. Wait a minute. Well, there's no sound coming.
Yeah, okay.
Sound should be on. I don't know why it isn't. But what he's doing is he has two objects, and the waves from the two objects interfere with each other. And sometimes the crests add up, and you get a big high crest, and sometimes the crests and the troughs add up, and you get a lower one. And that's called interference. And the device that I described works on the basis of interference of waves. So let me show that, how that works. So here's some waves. It could be any kind of waves. And in this left one here, you can see that there's two waves and they're lined up so that they add up. And here, there's two waves, but they're out of sync. So you get a middle. That's the interference that you're looking at. Okay, and here's one with water waves. This has got to work. And now watch what happens. You see, there's an incoming wave, and it's reflected so that there's an outgoing wave. There's the outgoing wave, and it meets the next incoming wave. And the place where they meet, there's a maximum interference. Okay? So this was much better with sound, but anyway. So now it's probably not surprising that two waves add up together. And I don't want it to be surprising. I mean these diagrams and so on look complicated, but it's basically a simple thing that waves add up. So here is the instrument that I showed, the LIGO interferometer sketched, and it uses light. Okay, so it uses light for interference. And what happens, I think I need a pointer. Just a minute, let me see that. So what happens is you have a laser light source, and these are visible or infrared lights. And it comes over here on something called a beam splitter. And what the beam splitter does is it breaks this beam into two parts. So half of it reflects off, and half of it goes through. So then this beam goes up to this mirror and reflects back down. And then makes another trip through the beam splitter and comes to the detector. The second beam goes through, goes to this mirror, comes back, reflects off the back of the beam splitter, and also comes here. Now, if these are exactly the same length, they'll be in phase. They'll be a positive. But if this mirror is moved slightly, then it may be out of phase. It could be a negative. So that's the interferometer. That's how the device works. So now, and the idea is that if a gravitational wave comes along, then one of these will be longer and the other shorter. And we can go in and out of interference as the wave bubbles through.
Why would the gravitational wave affect one but not the other?
It affects both, but it makes one longer and the other shorter. It's the kind of wave that it is.
How do you ensure the mirrors are distanced exactly right?
That's the magic thing of this thing. That's what took 40 years to develop. And I can't give you a simple answer. A lot of people thought it would never work, but it did work. Okay. So here's the gravitational wave coming along, and it moves this mirror by a tiny, tiny amount. Okay, and then there will be a change in the interference. And here's when the other one moves. Okay, now here we go again. This is a pretty good video, though.
The link is up on top.
Where am I not getting the? Oops. There we go.
No.
Okay. You see how the beams move? And that. Here's a detail. There goes the wave, splits into two parts, goes to the two mirrors, reflects back, hits the beam splitter again, and then the two waves may interfere at the detector.
Superposition is called.
So the degree of interference is determined by the movement of the mirrors.
But it's determined by the position of the mirrors.
Right, if based on position and movement of the mirror, whether or not they're moved or not.
No, you can move the mirrors apart and leave them stationary. And if there's a difference in distance, there'll be a destructive interference. If they're the same, it'll be constructive interference. Although you can also go an extra wave and it'll be constructive again, but that's complication.
Does constructive mean additive?
Yes.
Yes. Thank you.
You just have to give me time. I just, if I try to do this fast, I screw it up every time. So. Okay, well, I've already kind of said this. So just to remind you, now the reason this works, so remember, there's two kinds of waves. The thing we're trying to detect are the gravitational waves, but we're using light waves to do it. And part of the reason this works is that when you use light waves, the wavelength is just a 10,000th of a centimeter. So a little bit of movement, a fraction of a 10,000th of a centimeter causes interference. So, but that's why we can use light, because it has such short wavelength to make this work.
Still a big number compared with 10 to the minus 13, though.
Yes, it absolutely is. And it's amazing that they can say that. All right. Well, this was invented by Albert Michelson. And he originally, he didn't do this for gravitational waves. He did this originally in a famous experiment in the 1890s, which showed that the velocity of light is constant, which showed that fundamental thing. So he was, that was an amazing thing. I heard an interesting story about him. Somebody said that they were amazed when Michelson came. This famous physicist, did all this stuff. And he was at Caltech, and he was listening to things, and then he was starting to ask questions. And the person said, I could see that it was so hard for Michelson to understand things, to make progress, and he had to work so hard at it, that it gave me courage that I could do things too. Okay, well, so it was decided in the, if some of you saw the Black Holes movie that Doug recommended, you saw how they worked on those black holes. There was a similar thing here. There were a couple of teams, one at Caltech and one at MIT. And they both sort of had independent ideas that they should, that it may be possible to detect these gravitational waves. And they worked hard for, I think, something like 10, 20 years to do the theories, to do partial experiments to make things work. And then they went to NSF. And NSF supported both of them for a while. And around 1990, NSF, the National Science Foundation, came to them and said, okay, now you've competed, you've got different ideas, that's been very helpful, but now to make progress, you have to get together. You have to have one leader of the project, and you have to work together to build this thing. And they did. It was very, very difficult, but they did it. And so they decided to build two detectors, one in Livingston, Louisiana, and one in Hanford, Washington. And the reason for two is that this was so delicate and so difficult that they decided if we just had one detector, people would never believe it. They'd say, oh, you're just in some mess here. But if you see the same signal in two different places, then all the things that interfere with it, the movements of the earth, trucks rolling by, lightning hitting and stuff, all those things that interfere with the measurements won't happen in the same place in two different locations. So that's why the two were built. And at the same time, in Italy, they decided to build one as well. And everybody worked together in the end. So there were three that were ready to go in the early 2010s. Now, the other point I want to make is that we had this discussion earlier. The arms are 4 kilometers or 2.5 miles long. But one of the tricks they used was to bounce the light back and forth many times before they let it interfere. And that effectively made the lungs, effectively made them 1,200 kilometers long. Wow. So that made it made it more sensitive. But it was an amazing thing. And here is the whole 2.5 miles is in vacuum. Big long tube, got a very low vacuum because he couldn't have the light bouncing off of atoms inside the tube.
Roger, is there anything magical about the 2.5 miles? Why it's not 3 miles or 1.5 miles?
Money and they tried to make it as small as they could, where they thought they could see it. And here's one of the mirrors. It has to be suspended wonderfully so it doesn't wave when there's an earthquake or when there's a truck driving by and so forth. Very high technology. And well, this is another video just trying to illustrate the issue. And I got this idea from Rainer Weiss.
Oh,
Okay,
God.
so okay, so it's something I didn't know about our grandparents, and probably you didn't either. That they thought it was fun to spend a Sunday afternoon watching trains crashing into each other. And but the point of this is that one of the reasons maybe Einstein people didn't think we could ever do this is the kind of collision they were used to, right? Einstein did a lot of examples with trains. That was a violent collision in 1910. But this collision is nothing for gravitational waves, because if you compare the size of the strain that you get from looking at trains from 300 meters away compared to two black holes colliding 100 million light years away, the difference is a factor of about 10 to the 21, one with 21 zeros after it. Black holes that much bigger.
Question, Roger?
Yeah. Oh, well, let me finish. Make this point. they had success. 2015, September 14th, they saw these two signals, one at Livingston and one at Hanford. And this, what is happening here is that are two black holes spinning around each other, getting closer and closer, so the frequency gets higher, then bam, they collide into each other and it rings down and stops. And they saw the same thing at same time, fraction of a second off. So that was an amazing result. And so here's the picture. Here are the two black holes separated by, in this case, I don't have it here, but a few times their size. And then we begin to see them rotating around each other, and they go rotate faster and faster near the speed of light. This really happens fast. And then blam, they get together and they form one big black hole.
What force that makes them do that? So why are they circulating like that in the first place? And then how did they collide?
Okay, but they have some motion. They're circling each other. Because of the gravitational waves, they're losing energy, right? And that makes them get closer and closer together. And they radiate that gravitational energy. That's what we detect. But they get closer and closer together because they're losing energy in that process. Okay, now the amazing thing, so here are the two superimposed on each other. It's two called signals, but you had to shift the data by 6.9 milliseconds. And the reason for that is that they in fact are at different places, so that they arrive at different times. If they were perfectly perpendicular to both detectors, it'd be the same. But so this gives you a little bit of an idea of the direction that it comes from.
Was the Italian observatory not online yet?
That they had really bad luck. They were online and they were fixing it to make it more sensitive, and they weren't online for this first one.
Is there one planned for India?
Yes, there is one. Okay, so this is a really clever nomenclature. Gravitational wave, the 15th day of the 9th month of 2014. So that's how they're all noted. So the whole thing took about 0.45, half a second, when we detected it. The distance was measured to be 1.3 billion light years away. Hugely far away, but we're detecting this. It was possible from the shape of the signal to get the masses. There were 36 and 29 solar masses. Now, that itself was puzzling. We didn't know, and even now we're still not sure. How do you get black holes this big? Remember, I was talking about stars. The whole star was up to 36, 30, 40 solar masses, and it left a black hole of 5 or 6 or 7 solar masses. That's what we had time before. Now we have some really big ones, so there's an issue there. The final merged black hole had 62 solar masses, which means there were 3 solar masses lost.
Does the gravitational wave move through space at the same rate as light?
Very good. Virtually exactly to 1 part in a quadrillion. 1 part in 1,000 trillion. It's the same speed.
Oh, but not exact.
That's the accuracy we measured it at. Theory says it's exact.
Is there a difference in the gravity wave and the light wave wavelength?
Oh yeah, absolutely.
Gravity is a much longer wavelength?
Yes. Gravity waves can be any length. It depends on the process of the collision, the masses.
How were they able to infer the distance from
It turns out it's really neat that the timing of the signal and the shape of the signal and how it gets big gives you both the masses and the distance to the object. So it's cool. All right, here we go again. Maybe, back. What is it?
No, if it once.
So,
Yeah, there's a.
okay, so here's an impression of how, a mathematical impression of how it goes. These stars aren't moving around. They are being bent by the enormous gravity. The light's being bent. So we're seeing it moving as the black holes combine. This is slowed down. Remember, it takes half a second, this size, for this to happen. But this is what a black hole merger looks like.
Was there a lead up to that event lasting, some thousands of years if they got closer?
Presumably, but we can't detect that. We can only detect when it's really intense. Okay, now this is a different kind of a plot. There's a time across the bottom, and then they took the frequency, right? You saw all the wiggles, that's a frequency, and you can hear it. They put sound to it. So try this again. It should work. There. Oh, but I don't have sound, so it doesn't work.
Can you make the impression?
But this is more or less in real time. Okay. Okay.
Try it again.
Oh, there we go. There we go.
This.
Okay, that's the two giant black holes colliding.
Sounds like that.
Black hole merger ray. Get yourself on. Okay, so we have the two black holes. That was the tremendous result. Kind of complicated, I understand, but that was what was found. So let's take a break.
Concern about getting the videos?
Yeah, stop. Yeah. Yes. I've got kind of a long lecture, so I'm going to try to start again. Hold on. Okay. Text first. Okay. We ready to go? That's what we do. Crowd. Talk a little about the energy. A couple of questions came up. I mean, what the reason that these things spiral into each other, collide, is that as they're rotating around, they are losing energy into gravitational waves, into bending space time. And the amounts of energy involved are colossal, because comparing it to the sun, for example, the sun works by nuclear reactions. But the nuclear reactions, even though they're hugely energetic by our standards, only in the whole lifetime of the sun, less than 1% of the mass of the sun is going to go into energy. But in that half a second that we saw the two black holes colliding, 3 times the whole mass of the sun converted into energy. So it's colossal.
Yeah.
It's shaking the universe. So again, to compare, you know, a hydrogen bomb, a big bomb, converts a few grams of matter into energy. No, there's the E equals mc squared. I don't have time for all that, but it converts mass into energy, and it converts about a teaspoon or two of mass into energy. Mass disappears, and it's all the energy. But for this two black holes, it was 3 times the mass of the sun in the fraction, in most of it in the fraction of that second. So it's unimaginable. It's collision. It can hardly believe it puts us away. Okay, well, 3 people won the Nobel Prize in physics for this. When Nobel made his will, he made it that only no more than 3 people can share the Nobel Prize in a given year. They all have to be alive. So the 3 leaders, Kip Thorne was at Caltech, Rainer Weiss was at MIT. Rainer had really very early ideas about how to build a LIGO kind of thing. And Kip Thorne did an awful lot of the theory of what happens when 2 black holes collide, so on. And Barish was one of the team leaders. There was another one too, but it was one of the team leaders. And all 3 of them in their Nobel lecture, you can hear Nobel lectures on YouTube. All 3 of them were very careful to say, we didn't do this alone. Lots of people did this. It would not have been possible with just the 3 of us. It had to have hundreds and hundreds of people. And the paper, Observation of Gravitational Waves from a Binary Black Hole Merger, the first paper on this, well, Abbott by ABB got his name up there, but the et al. Was over 1,000 authors who were left below. Okay. And they all deserve credit for what they did. This was not a single person thing. One of the things I found interesting was Kip Thorne wrote a book in 1994 where he predicted this, and he talked about the project and its progress. And he also published this as a run-up. There's this part up here, and this is what he did in 1994, what he thought the collision would look like. And at that time, they didn't have the ability to solve these equations the way we do now. And so, where's my pointer at? And so now this is the part of the measurement, and part of it is the theory. In order to interpret what's happening, we needed the theory. So it took 2 or 3 decades to get the theory to the point where we could really understand what was happening, get this almost perfect agreement. So here they are lighting. I showed that before, but here's some numbers. The separation is here. So it started at about 6 times the Schwarzschild radius, and then came back, and here they collided. And then the speed, that's here, it's 3/10 of the speed of light up to 6/10 of the speed of light we're using. So it's really happening fast. They're giant black holes, and they're really going fast.
Roger, how prevalent are ordinary black holes?
We've seen about 300 of them in the 10 years since this was done. So anyway, right now we have these 2 LIGOs. There's the Virgo in Italy. There's the Geo in Germany, which actually is more of a test and development site. And India is building a LIGO. And Japan has an operational LIGO as well. They call it Kagra.
So is this the preferred way to determine black hole masses?
Yes. Okay. I mean, certainly for this kind of an object. Now we can determine, and there were guesses before or estimates, like in M87, the stars and like and more clearly in the center of our own galaxy, stars rotating around the black hole enable us to measure the mass of that black hole. But that's a single black hole. These are colliding black holes. So here's just a couple of pictures. This is the other two sites. This is Kagra. They decided to go underground and to get for more sensitivity. So it's a big underground tunnel. And then the GEO in Germany is actually not detecting black holes right now. They did a lot of the development work for the LIGOs, was done here and tested here. And they are now developing this into a LIGO type machine that will work at higher frequencies than what we have now. So it's an international effort. And here's a whole bunch of them. Like I say, we've seen about 300, something like that now. Here's a whole bunch of signals. And you know how to interpret this now. So that's, you get the date, and you can see that they're different masses, different distances, different types.
You know what the greatest distance away one has been detected from?
I actually don't know that. Yeah, I'd have to look that up. I don't know the greatest distance. But it's a lot. You can see these very far away.
Billions, like
Billions, yes. Okay, now here's another graph. This is kind of complicated, and if you don't get this, it's not that much. But the idea is the mass is plotted here. So the idea is, for this example, we have a black hole that starts at something like 65 or so, if I read it right, solar masses, and the other one at something like 85 or 90 solar masses, and they combine and they form this big thing, which is at 140 solar masses. So that's what and this shows a whole bunch of. Oh wait, I have a video that I made. Watch.
Roger,
That's what it does. Yes.
why, when they combine, isn't it just the sum of the two black hole solar masses?
Because they radiate. They lose energy when they're doing this. See?
Okay.
Okay. There's no way to prevent that. They're giving off that energy. And that's how we detect them. We detect that energy. Yeah.
The signal that we can hear, it's in the audio range. In terms of that signal that's detected by the LIGOs. But you mentioned that they're spinning at nearly the speed of light, or they're kind of, is that right? They're wrapping around each other at nearly the speed of light.
Yeah. It still takes a fraction of a second to go around.
Oh, that's so big.
They're big.
Hey, Roger, of this 300 plus collisions, is the energy released the same in all collisions, or does it depend on the total mass combined?
It depends absolutely on the mass of the objects, their sizes.
And what are they inferring about the universe, other than saying a lot of these things happen all the time?
I'll get to that in a minute. Okay, what we'll be doing with it. Yes.
What we see as single black holes now, is there any way to see if they had combined previously?
So,
Like if they hadn't?
Okay.
and he.
Question was, we see a single black hole now. Is there any way to determine if they have combined previously? And the answer is very probably they have, because we see black holes which are not just 20 or 30 or 50 solar masses. We see some that are billions. It's not clear how they grow that big, right? If you have like an M87, the black hole, which is 7 billion solar masses, I mean, it would have to swallow one star a year for 7 billion years. That doesn't seem really likely. What we think is happening is there are big collisions and lots of collisions going on. But that is a subject for research right now. That is absolutely at the forefront of research. So I'll take a couple of questions in a minute. So this was the first detection of a black hole. It's an entirely new way to do science, right? Almost all of our knowledge of the universe comes from electromagnetic waves. from visible light, X-rays, gamma rays, radio waves, infrared waves. But this is an entirely new way to look at the universe. These great waves go right through the universe. They're not stopped by things. And I'll get to, Will can tell us more about the universe. I'll get to that. Okay, so that's the gravitational waves, lots of black holes colliding with each other. Now I want to go to another kind of collision that we detect with gravitational waves, namely neutron stars. Remember, neutron stars, talked about those in the second lecture. They are these remnants of massive stars, and they typically are about 10 kilometers size, city size. So here's one over San Francisco. And they're an amazing thing. They are a solar mass concentrated down into 10 kilometers. And now, if two neutron stars collide, this is what is likely to happen. And can I make this one bigger?
Top left.
Oh, yeah. And you see, there's light now because they don't do all the gravity. Boom, you go. Okay. Let's see. So that is a artist's rendition of what that happens.
What? Yeah, what's left? That.
And in 2017, saw LIGOs and Virgo saw a gravitational wave from two neutron stars collide. This is the frequency signal, the chirp signal, right here. Notice it's longer, several seconds. Doesn't go as fast as black holes. And so here is where the two combined crashed into each other. And at the same time, a different detector, gamma ray detector. Gamma rays are X-rays, which are even more dangerous than X-rays. And 1.7 seconds later, there was a signal from the gamma rays. Because you see, neutron stars leave the light go. So see that.
So after they launch, they release light, not so massive.
There is how the signal proceeded. Then second afterwards, we saw the gamma ray pulse.
Is that different, the difference between the speed at which gravitational waves travel and light travel?
Well, I'll get to that in 1 minute in the next slide.
Bottom right.
Is the result of larger?
The result's a black hole, we think. Yeah, you can't, the neutron stars have an upper limit of about 2.3 solar masses. And so when you get two solar mass neutron stars, which is comparable to what here is, you really can't make it that big a neutron star. They end up as a black hole. Pretty certainly, anyway. Okay, just one second. Let me finish this idea. At the same time, we saw this gamma ray pulse. We could tell where the gamma rays and the gravitational waves were coming from. And it was in the direction of this galaxy. And bam, the star went off. That is the explosion of the neutron star. See. So now we see things. So it's really cool. This wasn't that far away, 120 million light years.
20 million years ago.
Yeah.
That's all I want.
Yeah. But by this time, the universe is big and it's old. So we have to adjust our thinking a little bit here, right? So 120 million light years isn't that far away. We're seeing things that are that are 13 billion light years away. So 120 million years is kind of our neighborhood. Now, one of the amazing things we got from this neutron star is by analyzing the light after the collision, we could detect that there were major nuclear reactions happening in that explosion, just like major nuclear reactions happen in a hydrogen bomb explosion. And we were able to detect that, in fact, what was going on is that elements like carbon and nitrogen and iron, and similar things, were being converted by nuclear reactions into the heavier elements, such as gold and silver and mercury and others. So this is a tremendous step forward in understanding. Now I'm going to do something somewhat complicated, but just bear with me if you don't get all this. But in my cosmology course, we talked about this. This is a graph of the abundance of the elements in the universe, how much there is in the universe, just letting hydrogen be one, the most abundant thing, and everything else is a fraction of the hydrogen, versus the element, which is the atomic number, the number of protons in that element. You can see the simple ones are the most abundant, and then with a lot of wiggles, there's a gradual decrease towards the heavier ones. So things like uranium and gold and silver are rare compared to things like oxygen and neon, which themselves are rare compared to hydrogen in the universe. So now we knew, and I pointed this out, that hydrogen and helium basically are reactions from the first minutes of the Big Bang. That's when all the helium is made. But the carbon and oxygen and nitrogen, we knew were made in stars. The sun is doing that right now, and will do it even more as it gets older. So these elements, all the way up to iron, are made in stars. And if you look here, I've circled it here, it decreases, and then it suddenly increases. Iron becomes much more abundant again. And so this is the iron peak. And the reason for that is that for reasons that have to do with the nucleus, these elements can all combine in nuclear reactions and give off energy, power stars. So in addition to transforming from one element to the other, they give off energy, like the sun is giving off energy, like the stars are, it's making the stars shine. But that stops at iron. Beyond iron, you can't make nuclear reactions that give off energy. You have to pump energy in it to make it work. So it's always been something of a mystery of how did these heavier elements form? And the way people thought of it, and I think correctly in the end, is that it takes neutrons to do it. These heavy elements are all rich in neutrons, and you've got to have a big, huge flux of neutrons to make it happen. And people always thought this is going to be in supernovae, and some of it probably is, but from the neutron star collision, we now know that neutron stars are really important in doing this. Because when the neutron stars collide with each other, it's full of neutrons. And that enables these elements to absorb neutrons and form things like gold and silver and iron and uranium and stuff. So that is an enormous step forward. Now, this is quite complicated, and there's a big story here, but I'm just trying to summarize it. And this might bring back happy memories from a chemistry class or nightmares. So this is a slightly different periodic table. It's a list of all the elements by abbreviation, so hydrogen, helium up there, and so forth. But what's here is this tells us by the colors where these elements came from. And the blue came from the Big Bang, first minutes of the universe. But things like carbon and nitrogen, C and N, they were formed in stars like our sun. In our case, the carbon and nitrogen that makes you up, that was formed in low mass stars similar to the sun billions of years ago. But then when you look at things like gold, this is merging neutron stars. And silver, Ag, merging neutron stars. Mercury, half merging neutron stars and and half low mass stars. So it's complicated, right? But so if you're wearing a gold ring, you are wearing the trace of a neutron star collision that happened billions of years ago. So we're part of the universe. So this, I think this is an enormously interesting development, and it's very much a part of research. I mean, right? We just detected this thing in 2017. There's lots to do, more stars to see, and so forth.
What's the gray area?
The gray area, these rays,
Yeah.
these are highly radioactive elements, and they don't occur in nature. We have to produce them, and they die very quickly. Okay, like for example, radon is formed by the transmutation of uranium, decays from uranium decay, but radon decays very quickly, so it doesn't occur in nature, just as it's produced by uranium. So these are not elements found in nature because they have a short half-life.
So when the neutron stars collide, they give off light, and that is the light gives you the indicator of what gets generated, right?
Exactly.
Now, what happens to it? Is it like a black hole, a composite of all this gold and all this heavy elements?
No, those elements are being blasted into space. They're being ready to make new stars in the future. Okay, so but there is a black hole remnant as well. Okay, but that we're not seeing directly.
Roger, where does the gold get its photons and electrons? Get a whole bunch of neutron stars.
Well, they have nuclear reactions that form protons and electrons. Okay.
What happened to lithium?
A little bit of lithium formed in the Big Bang.
No kidding.
Yes, a little bit of lithium formed in the Big Bang, but then what happened in the Big Bang, early moments of the Big Bang, you had all these elements. They were forming stuff. Hydrogen was converting into helium, but then the universe expanded so fast that the reaction stopped. They couldn't find each other.
Roger,
Yeah.
going back to the collision of black hole, you mentioned that there's a giant black hole in the center of our galaxy that has been detected.
Yeah.
Have any other black holes been detected in the center or the area of the center of the galaxy that would indicate that there's going to be another combination?
Yes, there's been, and people have looked for that. I talked about single black holes in the center of the galaxies, but we found a couple of galaxies now that have two and one that has three black holes, and they're orbiting around. And we think that at some point these are going to combine and have a giant merger. But we're not talking about a merger of galaxies of, crummy 20-30 solar masses. We're talking about 1 billion solar masses. That's a really neat.
Like five trade line.
Yeah. Now, that I showed this before. I don't think I'll run the video again, but just remember that there was this thing here, and they were combined black holes, and then 1.7 seconds later there was the gamma ray flux. Now this thing was 120 million light years away. So, which is 1,000 trillion light seconds, and the two came within a second, within 1.7 seconds. So the speed of those two things is the same within one part in a quadrillion, 1,000 trillion. We don't know of anything that accurate or that close besides
Was the
that.
light always just the little second one, or was the light the first one? Or
The light was the second one. And it's probably even better than that, because what we think happened with the light is that light pulse actually has to go through the debris of that explosion. And the light bounces around a little bit, and it takes it more than a second to get out. So that the two are the same speed. I mean, we definitely know there is the speed to within a quadrillion. So that is one of the things we've now learned about the universe. I mean, Einstein said that this would happen, but now we know it. The point is, it's a way, I think, to me, of thinking of the light speed. The light speed isn't something, just a speed that we have, like driving 60 miles an hour to San Jose. It's a property of the universe. It's a property of space itself. It's built into space, as is the gravitational wave speed. So somehow space in the universe has this built-in limit. That's how space is built. Does that make sense to you?
So there's an optical component to neutron star mergers. Is there an optical component to a black hole merger?
No, never seen. And people look, we haven't seen that. There could be a faint one because black holes may have junk swirling around or something like that, but we haven't seen that. Okay, so now I'm not going to be able to get into this at all, but I'll just mention it to you. Another thing about the interior of neutron stars, that's under the green there. This is how people think the inside of a neutron star may be. It's not all neutrons. There are protons and electrons in it as well. But it has a very thin atmosphere, and then it has a crust, and then and here it has protons with neutrons, and here we're not even sure. And the point is, this is so extreme. The gravity is so gigantic, and the pressures are so unbelievable that the center of the neutron star is a more extreme situation in some ways than the center of than a nucleus of the atom itself, because the nucleus of the atom, it's all put together by these incredibly strong nuclear forces. But in addition to those, the neutron star has this enormous gravity pushing down. So people are now trying to understand what is the nature of neutron stars. Are there new particles, even new kinds of forms of matter that form under these conditions, which we don't have in the laboratory, which we don't even have in the center of atoms? So this could tell us more about elementary particle physics. And one of the interesting things, in a way to think about this is how do we do a physics experiment? How do we learn what's inside a proton? Well, we crash two protons into each other in a accelerator and see what comes out. And in a way, that's what we're doing here. We're crashing two neutron stars into each other. Well, there you go. We're not doing it. And then we see what comes out. So this is a way to probe neutron stars and types of matter that we're just not familiar with.
When black holes collide, you said that a tremendous amount of energy is dispersed. Is some of that energy in the form of neutrons and protons that will become heavy elements?
No, they're not getting out.
It's all gravity.
It's gravity waves. That's where the energy is. But again, I can't say that 100%. There may be some junk laying around that's pushed around, but the basic idea is gravity waves.
I think some of them at least have a really huge magnetic field.
Yes.
Yeah. What creates the magnetic field on stars?
Well,
the spin of the neutron themselves.
Yeah, the question is what creates the magnetic field in the neutron star. That's getting us a little bit off, but look, the sun has a magnetic field, just like the Earth does. And stars generally have magnetic fields. We can measure that. And they're spinning. When this all contracts to become a neutron star, the magnetic field is drawn in with it, just like the matter is. The magnetic field is coupled to the charged particles that are drawn in. And that causes that's the origin of the huge field. But then it gets very complicated. A neutron star is spinning in millisecond rates, and the field gets tangled up. And it's complicated. Yeah?
Is there any relationship between all of this incredible mass, neutron star and elsewhere, dark matter?
And dark matter. Maybe. In this instance, we're not talking about it, though. We don't think that the dark matter gets pushed into the black holes.
How about dark energy?
No, we think dark energy is a universal problem of space. It may all be connected. We just don't know much about dark energy at all.
That's a lot of energy.
Lots of energy. That's right. And we're talking about unknowns at this stage. This is forefront science. And it's probably stranger than we can imagine.
Sounds like another course.
Okay, so the mergers, they explain the heavy elements in the universe, get an idea of the mass and sizes of neutron stars, strain their structure. They let us explore neutrons, protons, or even more exotic things than quarks. And the state of the matter. And there's some of you may know that something called superconductivity, that matter electrons in certain metals lose all resistance, flow forever without resistance. Superconductivity. Helium has a similar thing. Some people think neutrons might do the same thing. And where else? Maybe in a neutron star. Who knows? And we have confirmed this thing about space. Okay, now this is also a little bit complicated, but I actually wanted to show it because I think it's sort of artistic in some weird way.
Beautiful.
Okay. We're plotting the mass these objects again in terms of solar masses. I mean, you're all here when we talk about solar masses. We're always comparing the mass of the sun. If I did all this in grams, be a little bit confused. And so this is the same graph as the one I showed. The blue are black holes, and so this black hole at this mass banged into this black hole at this mass and formed this black hole. And so these are ones that we have detected so far, all the blue ones. So you see there's lots. And now, so that's the blue holes, gravitational waves. But remember, we also detected black holes like in Cygnus X1 near bright stars. The black holes not combining, but single ones. And those are plotted in red here, their masses. And here. And notice that they sort of start here. Then in addition to that, we have neutron stars, which are in yellow, because we detected those as pulsars. You can see here are the masses. They're all less than 2.3 solar masses. That is the theoretical limit. Beyond that, they become black holes. So that kind of makes sense. And then these orange ones are neutron star collisions. Pretty rare. We haven't seen many of those. And they form two neutron stars and forms a black hole, we think.
What's the lower limit of a neutron star mass?
The lower limit is about 1.4 solar masses. So that's the upper limit for white dwarfs. And then white dwarfs, if you get over 1.4 solar masses, they collapse. They cannot maintain themselves, and they can form a neutron star or an explosion, and then a neutron star. So this kind of makes sense. One of the things to note here, and this is not sure this is real, but notice there's not a lot here between 2 and 5. There's some, but not a lot. This has been called a mass gap. But we need to be careful about that because those things are hard to detect. If they're there, we're not sure that this mass gap is real or not. We'll think it is. So that's how stars end. But again, so far we're finding 100 and 200 solar masses. Okay, so that's kind of where we are. Now I'm going to talk about what's going to happen in the next 10 years. This is called LISA, Laser Interferometer Space Antenna. The idea is that instead of an interferometer on Earth, we're going to have 3 collectors in space. We're going to measure the distance between them very carefully. As a gravitational wave comes by, it's going to change this, and we get interference. That's the laser interferometer space antenna.
Wow.
And but instead of being just 2.5 miles across, it's going to be 2.5 million kilometers. So it's really big.
Ground points or something.
No, it's going to just not in the ground point. It's just going to follow the Earth around orbit in the solar orbit, in a sun orbit, in the sun orbit. This thing is big. And so now remember, we talked about this billion solar mass, 5.6 billion solar mass object in M87. And so there's what's going to happen here is that the fastest that anything can move, including black holes, is the speed of light. So when these 20 and 30 solar mass black holes close together, it's a fraction of a second. But for a billion solar mass thing, it's bigger than the solar system. The solar system is about a day across. Okay, one light day across. So the frequency is going to be not fractions of a second, but days. So collision is going to take days in this case. And for that, we need this kind of a large interferometer. And for this will enable us to see, if it happens, collisions of billion solar mass black holes. Now we don't know how black holes grow to billion solar masses, but one way might be that through galaxy collisions. If our galaxy collides, say with Andromeda, which actually is happening, we have a 4 million solar mass black hole in the center of our galaxy. The one in the center of Andromeda is somewhat bigger than that. And when our galaxies collide, those black holes could collide and merge. Then we'd have a really big merger. And we know galaxies collide, but we haven't seen that kind of a merger. Here's another case. See, and it's a disruptive event when galaxies collide, and it'll mess our galaxy up. And but the LISA will be able to detect this kind of mergers. So it'll detect black hole mergers anywhere in the universe. It'll see supermassive black holes. It'll see black holes and newly forming galaxies in the early universe. And I'm going to talk about that next time. And what it'll also be able to do is that it'll be able to see objects at the edges of massive black holes. And we will then see objects in extreme gravity in detail. And that will tell us more about both quantum mechanics and gravitation and gravity. So it'll be a big step ahead.
But are they going to control the space between the pieces?
Are they control the species? They have to control them super precisely. And they have already done a test thing. They launched in 2015, they launched a test case, and it worked perfectly, worked better than they expected. So they're pretty confident this is going to work. So, well, here, somebody asked me where it's going to be about 50 million kilometers behind the Earth. It's going to kind of follow Earth around in its orbits like this. And so 3 satellites.
Is this like an international consortium?
Yeah, it is. Here's the answer to that. It's actually led by the European Space Agency. The European Space Agency has most of the countries of the European Union as members of the European Space Agency. And NASA is an active partner in it, but it's actually being led by ESA. And this, like I said, this worked really very well. So they think they're now projecting a launch in 2035.
What's the 15 inch?
Pardon?
What's the 15 inch? Technology's 15-inch.
It's an interferometer.
That's
They
how
tried,
big that thing is?
that's how big the test was.
Oh, the
Not-
test.
Okay. They launched a single satellite, and tested out this idea.
And the tolerances on the final product?
You'd have to look that up.
Small.
Oh, yeah, they're gonna have to find small things, yeah.
Roger, is there a website or some other source where people can just find out what's going on right now, what they're planning or what
Or Lisa, yeah, just search Lisa on Google.
Lisa on Google?
Yeah, or use laser infrared, this acronym, you'll find immediately what they'll have.
They must have Utah to be able to send a beam that far without spreading out.
Yeah, they'll have a very precise lasers. So it's amazing thing. So that's the future. Okay, well, I'm nearing the end here, so you can remember gravitational waves are a new way to look at the universe. Emerging black holes are direct detection of black holes. We see neutron star mergers, it gives us insights into the elements. We have fundamental insights into the end states of stars as neutron stars and black holes. And black holes must merge or form somehow very massive black holes, but that is not well understood. So let me just give it a thought. When Galileo was the first one who had an astronomical telescope around 1609. And he first saw the moon, he saw the craters on the moon, he saw the phases of Venus, saw the satellites of Jupiter. But with that first telescope, by the way, this is a reproduction of what his telescope looked like. This is an actual lens from his telescope, Museum in Florence. But nobody could know what the future would bring with this instrument. Today we have telescopes that are 39 meters in diameter, whole of astronomy thing. And now we have a whole new way to look at the universe, these gravitational waves. And we're just at the very beginning of this. So who knows what the future is going to bring? Who knows what these gravitational waves will do? Detectors will do in 100 or 200 years or so. And it's a fundamental new way to look at the universe. Nothing to do with electromagnetic waves, gravitational waves.
Question? Is there gravitational wave noise radiating around the universe all the time?
Absolutely. There is. The question was, is there gravitational wave noise around the whole universe? And there is, and it's possibly been detected. And what it is, it's like a background. When you look at ocean waves, you see some big waves, and some waves have names and everything, mavericks and so on. But also you see all this waving stuff, little waves. You know that somehow that has to do with the wind and with things happening in Alaska and South America, and it all adds up. Well, that must be happening with gravitational waves as well. And people have looked for that background, and we now have a tentative observation of it. And I'll talk about that a little bit next time. Okay, so that's the end. Next time, I'm going to be talking more about supermassive black holes and galaxies. We're talking about James Webb Telescope observations of the first galaxies in the universe. And these first galaxies formed very early in the universe already have big black holes. This is kind of weird. Pulsar timing arrays that'll be looking for the background. And Hawking radiation is something weird. Wormholes are even weirder. Okay, that's it. Thank you.
See that? That's when you